stage is yours.
Thank you, Julian, and welcome everyone. This is the MPS Axign Class-D Technology Deep Dive webinar. This is the second webinar in this series. Last time we discussed a technology overview showing you the benefits of post-filter feedback, and today I want to get into a bit more detail. So today we will start off with a short introduction, and I will shortly recap post-filter feedback in Class-D audio. And then we will dive into the low-latency ADC. This is really one of the cornerstones of making our feedback loops. Then I want to discuss the configurable digital feedback loop. There's a lot of knobs to turn, but there's two things I want to talk about in particular: the ADC configuration and the digital loop filter configuration. Finally, I will discuss pulse width modulation in a bit more depth and end with a summary and conclusion. So just a short introduction. Axign is a fabless semiconductor company based in the Netherlands. And in the Netherlands, we have two locations, our headquarters in Enschede and a location in Nijmegen. So both are on the German border. And there has been a long relationship between Axign and MPS already for many years due to the very complementary IP we make, where Axign traditionally makes the mixed signal audio controllers, MPS makes a lot of the peripheral components, like power stages or DC-DC. It was a logical step for MPS to acquire Axign, which happened in the beginning of 2024, so this year. And this is captured nicely in the following statement. Axign is excited to announce that we are now part of Monolithic Power Systems. Our unique audio technology and expertise, coupled with MPS's manufacturing, product breadth, and system-level expertise, will enable us to offer industry-leading audio solutions without compromise. So a bit about me. My name is Olaf van der Meer. I'm a business development manager at MPS Axign, and I have a background in Axign's applications and customer support team. So let's dive right in. Post-filter feedback in Class-D audio using the MPS Axign technology. So in Class-D audio, we are dealing with switching amplifiers. An input signal is fed into a modulator, creating a pulse width modulation or pulse density modulation stream. And for the purpose of this presentation, let's assume PWM, because it's most common. But we're not just talking about any Class-D audio, we are talking about post-filter feedback. And this implies that we are taking a feedback point behind the output filter, as seen in the third picture. And this is in big contrast to traditional Class-D with feedback, where a feedback point is taken before the output filter. And the reason to take feedback is to suppress noise and distortion in the forward path. The forward path being anywhere between the input and the feedback point. And this can include errors in the modulator, for example, quantization noise when making PWM signals. And this can include errors in the power stage, for example, dead time distortion. When we take post-filter feedback, we can also correct for errors in the output filter as well. So this includes, for example, the nonlinearity of the inductor. We can suppress this type of distortion. It should be noted that THD plus N, so the total harmonic distortion and the noise in the feedback path, cannot be corrected, and therefore high quality feedback is key. So in the analog domain, if you want to make such a system, the parameter spread of analog components will present a limitation. And when we go to high order designs, meaning very aggressive filters, we have very small margins of stability, and we cannot afford to deal with parameter spread. And therefore, MPS Axign uses fully digital feedback loops, which are consistent, meaning there's no parameter spread, and they are programmable, which means we can easily tweak them or update them for every application. And these digital coefficients are loaded on startup. So the programmable feedback loops, for example, can be fine-tuned to meet certain performance requirements or meet the lowest power dissipation on a system level. And ultimately, and this is really a key takeaway, the quality of the feedback system is limited by the quality of the feedback path. And therefore, a high-resolution analog-to-digital converter, or ADC, is required. And we can see that in the block diagram here. So this is the Axign controller. And very central are the PWM control, our loop filter, which determines the feedback loop dynamics, and our high-resolution ADC, which digitizes the feedback signal. And this patented ADC technology is a cornerstone of Axign technology solutions. And that's why I want to dive a bit deeper into it in this presentation. So in practice, you can make such systems using, for example, the AX5688 and the AX5689. And these are respectively a 2-channel and 4-channel controller for post-filter feedback. And you can use these together with, for example, power stages and DC-DC available from MPS. So a very typical, say 4x25 watt system, if you're making a soundbar, for example, could be the following, where you use a 4-channel controller, the 5689, and 2 stereo power stages like the MP8049S. It should be noted that the 5688 and 5689 are what we call power stage agnostic, which means these controllers can work with pretty much any power stage. And it also should be noted that more MPS Axign products are in development at the moment. So let's get into a bit more detail, and let's look at the block diagram of the AX5689. What do we see on the inside? We see that a lot of components are parallelized, and there are multiples of them in the digital architecture. For example, there's 8 PWM blocks, there's 8 loop filters, and there are 8 low latency ADCs. Furthermore, we see an output crossbar for easy routing, power stage control, we have mode control, for example, for muting, and we have a control interface, and the device can communicate over I2C or SPI. It can accept an I2S input stream or output an I2S stream. One of the interesting things is also that the common mode and differential mode are separated internally. And we will get into the reason for this later on when discussing the ADC. There's also a possibility for PWM feedback, for example, to make inherently stable loops. And one thing you might have noticed is that the ADC has 2 inputs. So let's get into a bit more detail for the low latency ADC, or LLADC as we call it. So the 5688 contains 4 of these, and the 89 contains 8 of these. And why do we have so many of these ADCs? Well, primarily it is because we can parallelize them, place them next to each other to get higher performance. So here on the pinout, we can see what this looks like. This is the 5689 with 8 low latency ADCs, and they all have 2 inputs each, which means 16 pins are used. So we have 2 inputs, which means they are differential input ADCs. And why do we have this? Well, primarily it's to be optimized for bridge-tied load operation. So this means that we are driving both sides of the speaker terminal and not having one to ground. The reason to use bridge-tied load is to make a larger signal swing when we make 2 signals in antiphase with a potentially higher output power. But another nice benefit of fully differential design is to eliminate even order distortion. As noted before, we also have a differential and common mode split. So the common mode signal is determined by the average of the inputs of the ADC, and the differential signal is determined by the difference. So both the DM and CM, differential and common mode, have different performance requirements. The differential mode is actually what we hear. And this is a primary reason to separate these streams. We have different requirements for common mode and differential mode. So the ADCs are current input ADCs, which might seem like a remarkable choice at first, but it makes sense when you think about it. Using a current input ADC, we use these ADC resistors to convert any output voltage into ADC current. And by being able to scale these ADC resistors, this means the system is scalable for all levels of the supply voltage. Let's call that PVDD. In practice, what this means is that it's very easy to use such a system with, for example, different power stages, which might have their own different supply levels. You could make, for example, a woofer-tweeter split, where we have a woofer, for example, at 48 volts, and we use large resistors, and we have a tweeter at maybe half of that supply voltage at 24 volts, and we use smaller ADC resistors. So the digital control signal acts on the digital ADC output. So from a control loop perspective, both loops look pretty much identical. And this makes it very easy to scale these designs to higher output power. We simply increase the supply voltage and increase the ADC resistor proportionally, which means the digital output of the ADC stays the same. It should be noted that noise performance of the system correlates with the ADC resistors. So going to a higher supply voltage with higher ADC resistors will also result in a higher noise. And this presents us with a power-noise trade-off. Going to very high output powers will also bring a higher degree of noise. And one way of looking at this is saying that the dynamic range of the system is constant. So on the one hand, we are increasing the noise floor. On the other hand, we are increasing the maximum output signal. So the difference between those two, let's say the dynamic range, is a constant. So let's get into the configurability of these digital feedback loops using the 5688 and the AX5689. We have a flexible ADC configuration to leverage all the available hardware for a chosen topology. For example, with the 5689, we have 8 of these ADCs, and we could configure them as 4 times 2 ADCs, making a 4-channel system, or we could use a 2-channel system, both with 4 ADCs in parallel. We see this in the bottom. On the left, we have a 4-channel system, where we use 2 ADCs in parallel for every channel. And on the right, we make a 2-channel system, where we use 4 ADCs in parallel. In edge cases, you could even say, I'll put 6 ADCs towards my tweeter and 2 ADCs towards my woofer, for example, if the tweeter noise performance is more critical. The takeaway is that there's a 3 dB boost to dynamic range for every doubling of parallel ADCs. This is because the input signals that we are feeding into the ADCs are perfectly correlated, whereas the noise in the ADC is uncorrelated. So taking the parallel feed out of these 2 ADCs increases the performance by 3 dBs. And this is for every doubling, going from 1 to 2 to 4 to 8. So besides configuring the ADCs, we can also configure the digital loop filter slices. So we have 8 of these, what we call slices, loop filter architectures, next to each other. And these loop filter slices can be used to form several digital differential mode and common mode feedback loops. So a common mode feedback loop is not used to improve the performance. Common mode is not what we hear through the speaker. But common mode feedback loops are used to damp the output filter resonance. So the common mode LC response is typically not damped by the differential load. We can see that here, typical output filter, LC filter, the load is placed purely differentially. So for the common mode LC resonance, meaning both nodes of the speaker terminal are resonating identically, we don't have any damping from the differentially placed load. And this can cause a lot of current to run and a lot of power to be wasted. And one straightforward way of eliminating this is to use RC snubbers, Zobel networks, but this basically means we are just dissipating power to reduce this issue. Instead, using electronic damping with a feedback loop is a much more attractive way because we are not wasting any power. So we both eliminate the RC snubbers and Zobel networks, which is a cost down, but we're also making a more power efficient system. So that's why we make common mode feedback loops. As mentioned before, the differential mode signal is what we actually hear. So differential mode feedback loops are used to suppress audible distortion and noise. And that brings us to the last topic, the pulse width modulation. So Class-D is traditionally popular due to its very high efficiency, especially when going to its full output power. It's very common for Class-D amplifiers to reach about 90 to 95% efficiency. And this is a big contrast to old-fashioned Class AB amplifiers, where maybe an efficiency of 60% is more common. However, we recognize that 70% of the audio signal, roughly, is between 10 and 40% of the amplifier output power maximum. And this means that typical audio content contains very low average power. Sometimes this is described by engineers using the crest factor. So the losses at normal listening levels are largely determined by the switching losses of our amplifier and the ripple losses running through our output filter. Switching losses largely occur due to the parasitic capacitance charging and depleting, and the ripple currents run through both the power stage and the output filter inductors. And the issue here is that the maximum ripple for traditional Class D amplifiers occurs at low outputs. And this means that we are wasting the most energy at realistic listening levels, and we are not fully leveraging the Class D amplifier advantages. So how do we do this at MPS Axign? We address both the switching losses and the ripple losses with one solution. We call this zero common mode switching. And this requires a bit of explanation. So on the top, we see traditional Class D. Using a bridge-tied load, we drive two signals, one on the positive terminal and one on the negative terminal. I'll call them V plus and V minus here. And we drive them in antiphase. So the differential mode signal over the load is the following sine wave with twice the amplitude of these sine waves. The common mode signal is half of the supply voltage. However, when we go to zero common mode switching, it's very different. What we are doing is driving only one side of the output and then keeping it zero for the second half of the sine wave. And this means that only one side of the load is switching at a time. So here we have switching losses on the positive side of the load, and the negative side is completely zero, so we are not incurring any switching losses, and vice versa. The resulting differential mode sine wave is still the same as the traditional Class D. However, our common mode behavior, the average of the two terminals, is vastly different. We see that the common mode signal is always the minimum value it can be. So when we're not driving any output power, not driving any music, or driving very small signals, for example, in a realistic scenario, the common mode will be very close to zero, and it will always return to zero. And this is why we refer to it as zero common mode switching. So this is why it's beneficial for switching losses, only one side of switches at a time. But why does it address the ripple losses? And for this, we again have to compare BD modulation with our zero common mode modulation. On the left side, we see the traditional BD case, where in idle, so when we are not driving any output signal, we have a 50% duty cycle PWM. And the resulting ripple current through the output filters can easily exceed an ampere, in this typical case, 50-volt supply, 500 kHz switching frequency. But when we are using the zero common mode case, we are having almost zero at both sides of the speaker. And this means in the PWM signal, we are making very, very small pulses. And we have an extremely small ripple current as a result. So logically, this also eliminates the ripple losses for very small signals. So this sounds pretty great. We are addressing switch losses, we are addressing ripple losses. So why doesn't everyone use this type of driving? Well, traditionally, this type of driving power causes significant crossover distortion. And we see that on the right. So at these kind of knee points where we transition from one phase to the next, we have significant crossover distortion. Around zero, we expect the power stage to make tiny pulses and to be very accurate, and this is hard for power stages to do. It's much easier for them to drive 50% duty cycle. However, we know that the distortion in the audio band is eliminated by the extremely high loop gain in the Axign MPS feedback loops. It's easy to make a loop more than 60 dBs throughout the entire audio band, which makes this crossover distortion negligible. As a result, a THD plus N number well below 0.005% is possible, as seen on the right. And this is frequency independent and load independent. So using this type of driving output power, we are combining extremely low losses with extremely high audio quality with no compromise. So how do we configure these PWMs? As seen before, the AX5689 has 8 configurable PWM outputs. And this means we can make a number of flexible configurations. For example, 4 times the bridge-tied load configuration, the most, let's say, cost-effective solution. So we require 2 PWM outputs because we are driving 2 sides of the load. So with 8 PWMs, we can make 4 bridge-tied load BTL channels. but we can also do 2 times what we call parallel BTL, PBTL. And then we are using 4 PWMs per channel. We can also make a combination, for example, 2 times BTL and 1 times PBTL, which could be interesting, for example, for a small monitor speaker, having 2 tweeters and 1 woofer. And the reason to go to PBTL is typically for the higher output power. So here we see an example using the MP8049S. So this is a stereo power stage and it has 4 PWM inputs. So we could either make 2 times BTL with this or 1 PBTL. So when we are using 4 PWM outputs, we can use a type of 2-phase modulation or what we call 4-phase modulation. And this 4-phase modulation is an advanced option for the absolute highest performance. Again, it's only possible for PBTL because it requires 4 PWM outputs. So I'll shortly get into that. For 4-phase modulation, we generate 2 more digital PWM carriers that are 90 degrees out of phase with each other. So in a traditional case, for a BD type of modulation or for our zero common mode, we would have 2 carriers that are in opposite phase of each other. And we would call this a type of 2-phase modulation. But for a 4-phase modulation, we generate 2 more carriers that are 90 degrees out of phase. And this type of system has a much higher performance, but the downside can be seen here. We have an inductor per half bridge. So where normally we had 2 inductors for a BTL channel, now we have 4 inductors. So the currents here are summed behind the inductors, and we can see that nicely in the plot here. All the inductors have a pretty low current running through them, and the sum of all the currents creates the output signal. So we could also make a 2-phase system, and we could sum the currents before the inductors. This would still mean we have double the available current. Both power stages are still able to drive their full output current, and we can go to very high output powers. And we only need 2 inductors, but we don't get the performance benefits. So in the 5689, we have 8 PWMs on board, so we could make 2 4-phase systems or 4 2-phase systems. And for the 5688, it is half of that. And that brings us to the summary and conclusion. So we have seen that we have fully digital feedback loops, and we have chosen this type of topology because there's distinct advantages over analog feedback loops. In particular, they are consistent, there's no component spread in digital feedback loops, and they are configurable and programmable. Both the differential mode signal and the common mode signal are controlled using digitized feedback. And this differential feedback loop is used to suppress audible noise and distortion, but the common mode feedback loop is used to control the LC resonance, so the output filter common mode resonance. And this eliminates the needs for snubbers for Zobel networks. We've also seen that we can use a type of output power driving, zero common mode modulation, which allows for extremely low losses. And the reason we can do this is because we have a high order feedback loop, which guarantees the exceptionally high audio performance because of its high loop gain. And if you want to go to the absolute highest performance, we have a 4-phase modulation, but this comes at a higher system cost because we need 2 extra inductors. So it is clear that this is a very highly configurable digital architecture. We have configurable ADC configurations where we can place multiple in parallel for higher performance. And this makes it easy to just place any number of ADCs until you meet your noise specification. We also have configurable loop filter slices, which we use to make differential and common mode loops. So in the 5689, which is a 4-channel controller, we could make 4 differential mode loops and 4 common mode loops. Then we also have a configurable PWM modulator and outputs, where we in principle always use this zero common mode PWM for extremely high efficiency, and we can configure it to 2-phase or 4-phase channels. So the high configurability creates a very high potential for optimization, but how do you easily leverage this for your application? Well, we know from experience that it's not the easiest to start tinkering on your own because there are so many knobs to turn. So instead we have MPS Axign reference designs. So these are copy-ready designs. You can just look at the performance and the output power levels and copy it to your own infrastructure. And these are already optimized by our engineers for best thermal performance, audio quality, and cost. Axign already has several reference designs available, but now being part of MPS, we are revising them and republishing them as soon as possible. And the best way to stay tuned is to go to our Class-D audio page and subscribe to our newsletter. There's a specific audio subsection, and we will update you as soon as reference designs become available. And that concludes it for today. Let's move on to the questions and answers. Thank you.
Thanks a lot, Olaf. Great presentation. So I want to remind everyone that you can mouse over the bottom of your Zoom webinar interface, and then you will see the Q&A button. Please type in any question that you might have. As we are waiting for more questions to come in, I want to remind you that we are recording this session and it will be sent out early next week. With the link we will send over, you can watch today's webinar on demand, and we will also provide you a PDF of the presentation. Please also check our MPS website and the webinar schedule to see additional sessions. So let's get started with the first question, and it is: a typical audio ADC will have latency, at best 0.1 milliseconds. That would be way too slow for this feedback application. How is this managed? What about linearity of the ADC?
There's, I think, multiple layers to the question. So first of all, the latency of the ADC. We have a low latency ADC designed that has a near zero group delay in the audio band. So this is extremely suited for audio applications. In terms of linearity, it is designed in such a way that it is not limiting. As you know, the linearity of the ADC cannot be compensated by feedback principles. So given the performance metrics of our amplifiers, for example, the THD plus N well below 0.005%, which is very common for our systems, we can see that this is not limited by the linearity of the ADC.
Okay, thanks a lot. The next one is, you mentioned that feedback at the output of the PWM modulator can also be fed into a filter slice. What are the advantages of this?
Yeah, so that's a good question. In principle, you don't want a system that only uses PWM feedback, but this can be a very convenient tool because a loop using PWM feedback is intrinsically stable. So one way we use this, for example, is to do a board bring up where we can use PWM feedback and the customer can just bring up their system. The performance is okay-ish, and it doesn't matter what you do in terms of load and output filter. The system is always stable and you can debug your own hardware. And then later on, we enable the ADC feedback with post-filter feedback, and then you really see the performance kick in. So it's not so much as an end application use, it is more of a tool that we can use during bring up.
Okay, thanks a lot. The next one is, what about availability? I have not been able to order the AX5588 so far.
Yeah, so that's a good question. So we want to share reference designs with you as quickly as possible so that you can start using these devices for yourself. So we are working very hard right now on making evaluation modules available so you can see the performance for yourself. Like I mentioned before, it is not the easiest to order, let's say, a loose device and configure all the registers yourself, because there's just a lot of them. It is a very highly configurable platform, which creates a lot of potential for optimization, but it's not the easiest to work with for the first time. And that's why these reference designs are such a great way to get going. So we hope to have the reference designs and evaluation modules available very soon. And I would say that's the perfect starting point to get started. Yeah.
Okay. Next one is, how long is the latency from input to output?
Oh, that's a good question. I wouldn't have a hard number for you right away. In principle, there's no processing at a low clock rate, which would normally introduce a significant amount of latency. So it is an extremely low latency path. But I wouldn't be able to give you one hard number for this.
Okay, next one is, where do I find information on how to configure the AX5689 and its internal filters? Is there a programmer's manual available?
So the datasheet does contain a lot of information about the registers, but as I mentioned before, it is really configurable and it's easy to miss one or two settings that will end in a lot of debugging frustration. So the best starting point is these reference designs where you can make small changes compared to the reference design to meet your requirements. I understand it's difficult because these evaluation modules and reference designs are not available at this moment. So we hope to share those with you very, very soon.
Okay, thanks a lot. The next one is, would you let me know the pros and cons regarding two-phase and four-phase modulation?
So the big advantage of the four-phase is a higher performance. And this is, for example, because the currents per inductor are lower, so the intrinsic distortion is lower. It's because of our PWM switching, where we have 4 carriers and we effectively make more decision moments per second. So I hope this is not too deep into the control theory. The takeaway here is that this four-phase modulation creates higher performance. The downside is that you need at least 4 PWM outputs and you need an inductor per phase. So you need 4 inductors where you would normally need 2. So in some of our, for example, high-end streaming amplifiers, this is a very popular option where having 2 more inductors is not a significant impact on the total BOM cost. And people are okay with this for the great performance benefits it brings. But on the more cost-sensitive sides, maybe if you're making a soundbar with a lot of channels, then it is more advantageous to take the 2 inductor option and go for a 2-phase system. So it's really performance against cost.
Okay, thanks a lot. Next one is, are there plans for power stages for 70 volts or 100 volt systems?
So for the higher output powers, we see a lot of potential in the discrete power stages. We've had a lot of success with these as well, using both MOSFET and GaN technology. It is very common to also have 100-volt tolerant MOSFET or GaN FETs, for example. So this is definitely possible, and our controllers are able to use these type of FETs. Yeah.
Next one is, have you considered making a sort of tool or GUI that would allow a user development engineer to tune configurations outside of the bounds of the reference design?
Yeah, so this would be ideal if there was a tool where we could give it to customers and they could configure the system totally also outside of the bounds of the reference design. But we know from experience that this, let's say, complex control theory is not very easy to grasp. And this is really where we stand now, the culmination of about 10 years of perpetual development. So in the future, we intend to make it easier to use for our customers, to also present a GUI and to make a more configurable system. But this is not something we can make available in the coming weeks or even coming few months. This is really on the longer term. So for the short term, we think the reference designs are the best way to move forward. But we are definitely on the longer term looking at making it easier to use for customers and presenting them with a configuration tool. Yeah.
Okay, thanks a lot. The next one is, are there application notes for tuning the feedback paths?
There are no public application notes for tuning the feedback path. It is very complex to take all arguments into consideration. For example, you could tune the feedback path in such a way that the performance seemingly improves, but then there will be an edge case that creates an unstable system or that creates otherwise undesired behavior. So in our company, we have developed a methodology for fine-tuning feedback loops in a very efficient way and looking at all these edge cases. And for a customer, it's very hard to consider all these edge cases when tuning a feedback loop. And therefore, we decided, let's optimize it for them and present it in the form of reference designs.
Okay, thanks a lot. The next one is, can we drive external PWM IC for higher power use like 80 volts?
Can you repeat that question?
Can we drive external PWM IC for higher power use like 80 volts?
I'm not sure what the external PWM device then would entail. If it means a PWM input device, yes, you can in principle drive any PWM input device, also going to higher voltages. So as discussed during the presentation, using the current input ADCs, we can use any type of supply voltage. This makes it really, really nice. We just scale the ADC resistors. So also a PWM input device up to 80 volts is no problem.
Okay, thanks a lot. Next one is, will some of your reference designs be with discrete output devices or will they only be with MPS devices?
Yeah, very good question. So yes, it will be with discrete devices as well. So of course, we will look at making a cost-effective system solution. And typically using MPS components gives us the most cost-effective solution. But there are also discrete power stages in this whole story, both on MOSFET and both on GaNFET. You can still expect this year to see a MOSFET and a GaNFET reference design become available. Yeah.
Okay, thanks a lot. The next one is, do you see an opportunity to do multi-chip module that would leverage MPS power stage with Axign modulator IC, like a high power chip amp?
Yeah, so making a multi-chip module could be one of the options. MPS is known for its expertise in packaging as well. So it is an interesting option to look at, combining Axign's original IP and MPS power stages, for example. So this could definitely be in the future roadmap, yes.
Okay, the next one is, would you let me know about operation temperature range?
So we have at this moment the AX5689 controller, for example, separated from the power stage. So typically the 5689 or 5688 does not heat up significantly. So it can easily go to temperatures well above 100 degrees, and this typically does not happen. So there is no issue there. The power stage, on the other hand, of course, does heat up when we are driving significant output power, but this is really a power stage consideration. So what we like to do is make heat sinkless designs, especially using our discrete output stages, discrete GaNFETs, discrete MOSFETs. We make all this heat sinkless, and then we simply have to tune the output power spec in such a way and design our feedback loop in such a way that we don't overheat these FETs. But it's very normal that we can drive maximum output power for a number of minutes.
Okay, thanks a lot. The next one is, do these ICs support ACQ100?
They do not. So I think you are referring to the automotive grade qualification here. These chips are not automotive qualified at this moment, no.
Okay, next one is, I hope that on the reference designs, the amplifier output to feedback ADC's input is not hardwired so that the end customer can use the reference design for output voltage or load current feedback.
So they are not hardwired, indeed. The reference design will have a block diagram to show you conceptually how the feedback lines run, and we can give a layout example of how we would, for example, do it. You can see this in our evaluation modules as well, but we certainly give the freedom to the customer to make their own layout.
Okay. The next one is, in the 4-phase example, load is driven at one terminal while the other is tied to G and D. Does this perform worse regarding dynamic range comparing to driving both terminals of the load with 2 phases?
Yeah, a good point. So the diagram indeed shows a single-ended load. In practice, we would drive it in a bridge-tied load configuration. For the sake of the example, it only contained one capacitor and a single-ended load. But in practice, you would see a bridge-tied load configuration. So very perceptive. Thank you.
Okay, next one is, do you have any design partners that can help us with a custom application for our engineering team?
So we don't have any partners. In principle, we have our own customer support team that can make custom designs. But of course, it is a, let's say, involved process where we tend to do these for larger products. If you're making a smaller product, the best way to go ahead is to use a reference design. And for the larger products, please contact your local MPS salesperson.
Okay, thanks a lot. So at the moment, I'm not seeing any new questions. I want to remind everyone that we have recorded this webinar, and we will send you a link to the recording and to the presentation in a couple of days. So we will pause here for a little bit to give you the chance to type in any further questions. So I'm not seeing any further question at the moment. So thanks a lot to everyone who joined today. Again, we recorded this session and we will send you the link in a few days. And I want to remind you as well that you should look out for future webinars on our website. And hopefully we will see you back here again very soon. Thanks a lot and have a great day.